So in the previous class, we learned about the memory instructions, right? So you need to understand how the memory instructions work. Also, how the how data are allocated in the memory. Okay, so those are important topics we learned in the previous class. Okay, so in this time, in the today's class, we will learn about some more the other instructions, and then also we will learn about the control instructions. Okay, so control instructions. So control instructions. This is the important topic. Okay, okay. Uh, the firstly, so let's learn how to generate constant. So constant is the constant number. So in the previous class, we learned about the immediate operands, right? So what are immediate numbers? So immediate numbers are small constant numbers included in an instruction. Okay, so immediate numbers can be included in the instruction, which means that this number, the immediate numbers are represented using two's complement number system, two's complement, okay? And then this number is encoded into the machine instructions, okay? So you need to remember that the size, the bit numbers used for representing this immediate number, the number of bits is 12-bit, okay? So immediate numbers are 12-bit two's complement numbers, okay? So you need to remember. So this is the example. So this is the C code. So we assign minus 372 to A, the variable A, and then we can perform the B equal A plus 6. So then how can we assign this number, the minus 372? So what is the size of 12-bit two's complement number? It's minus 2 to the power of 11 to the 2 to the power of 11 minus 1, right? So this is the range of the 12-bit two's complement number, right? So you know the minus 372. So this is this number is within this range, the range of 12-bit two's complement number. So we can just assign this small number, the minus 372, using the add I. So what is the add I? So add I is the immediate add. So this is the add instruction which uses immediate numbers. Okay, so as you can see, you can find that in S0 we store 0 plus minus 732. So which means that the S0 we can assign minus 732 to register S0. Then how about this one? We can simply use the small constant number using add I, right? So small constant number. So we can represent the small constant numbers using these immediate numbers, and then usually we can use the add I. But you need to remember that this immediate number is the 12-bit signed constant. It's a two's complement number. Then how can we assign large numbers? So sometimes we want to assign the very large constant number. So for example, we want to assign the 32-bit two's complement numbers to the, so it's rare. It's rare, but it can be possible, right? Then, in order to support the this operation, RISC-V has an instruction called the LUI. So, LUI actually store, so in the 32-bit RISC-V instructions, so actually the 32-bit integer type RISC-V ISAR supports the 32-bit registers, right? Okay, then we want store 32-bit numbers, 32-bit two's complement numbers to these registers. So in order to support this operation, the RISC-V has LUI, but LUI cannot store entire 32-bit numbers. So it is because, so we will learn about this instruction encoding later, but in a RISC-V, the size of a single instruction is 4 byte. So 4 byte, okay? So 4 byte is the 32-bit, okay? So I mentioned that immediate numbers are included in the instructions, right? So which means immediate numbers needs to be included in this 32-bit instructions, right? But in order to represent instructions, we require additional field. So which means that we cannot handle 32-bit numbers using instructions. So that's why we cannot store these large numbers in an instruction. Okay. So LUI just to support 20-bit immediate numbers. So it means the LUI puts 20-bit immediate numbers to a register, a target register. But it's a 20-bit is the upper 20-bit. So what does that mean? So this is the 32-bit register. So pin number 31 to pin number 0. Then LUI just store this upper 20-bit. So for example, 31 to 12. Okay, pin number 12. So LUI fills this amount of data. Then how can we fill the remaining part? We can use add I, right? So in the previous example, so I explained that we can put the very small, not very small, we can put small constant numbers to registers using add I. So which means actually add I just fill the lower 12-bit part to the register. Okay. But if we use the 0, then all the existing data was 0. But so, and then if a register has a certain value, then we can just add this immediate number to the data in the register. Okay. Then so LUI put the upper 20 bits part, and then using add I, we can fill the lower 12-bit part. Okay. So this is the example. So we want to assign this large number to the variable A. So we can split this number to the two parts, the upper 20-bit part and then lower 20-bit part, lower 12-bit part. Okay. So using the LUI, we can put the upper 20-bit part to the register, and then using the add I, we can put the lower 12-bit part. Okay, so by doing this, we can assign the very large number, it's a 32-bit immediate, the constant number, immediate number to the registers. Okay, but you need to remember that this number, is the 12-bit signed number. Okay, so what does that mean? So, and then what is the operation of this add-I instruction? Add-I instruction, the operation of add-I instruction is addition, right? So actually add-I performs, so S0, so read the data from S0 and plus 0x765, right? So actually using the LUI, when the LUI put the upper 20 bit to the register, then this low bits are all zeros. And then using the add I instruction, we can just add the lower 12 bit, like a 7. What happened? 765. So we can fill this part. But you need to remember that this is actually addition, and this number is signed number. When addition is performed by hardware, and then if this addition is a signed addition, then actually we need to apply sign extension to operands. Do you understand? So S0, the size of S0 is actually 32-bit, right? This is the size of a single register. And then the size of this immediate number, the immediate number used by add I, the size of this immediate number is 12-bit. Then how can we perform 32-bit number plus 12-bit number? Actually, we need to apply bit extension. So, but because this 12-bit number is a signed number, it means we need to apply sign extension, right? So you need to remember this. So, okay, because this is the signed number. Actually, the add add of instruction performs the signed addition. Okay. So then actually the 765. So this what is this number? This number is the 0111 0110 0101, right? So if we just check this 12-bit number, what is the MSB? MSB is 0. So what does that mean? This number is positive number. Okay, so if we apply the sign extension, then we can just fill zeros for the upper part. Okay, so in this case, we can easily generate this number. But let's see the next example. The next example, so we want to assign this large number to variable a. So what is the problem? If we just split this number to the upper part and then lower part, the lower part starts with the E, then it means it starts with the 1110, right? And then 1010 and then 1011. So what does that mean? So I mentioned that this low part. So when we use the add I, right? Add I, then the lower part is 12-bit signed number. So which means if we apply add I operation, then this immediate number is extended to 32-bit number, but we need to apply signed extension. So we need to fill the upper part using all ones. Then what's the problem? So in order to make this number, okay, this number, then actually it looks like this. So F, E, D, C, and A, it occupies the upper 20-bit, and then we need to perform addition, but F, 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 and E, A, B. So this is a 0, 0, 0 will be added. Then what's the problem? If we just use this number using for the LUI, then what is generated? So it will generate the FEDC7. Why? So actually this is the EAE. Why? So actually these are 0, 0 plus EAB is EAB, right? But this part, FFFFF. So the sound is not good. FFFFF. The all ones. So it is actually -1, right? In two's complement number. So if we just perform additions using FEDC plus all F, FFFF, it sounds bad. Then it is equivalent to FEDC 8 minus 1, right? Because this is -1. So what should we do? Instead of using FEDC 8, we need to use the FEDC 9. If this number starts with the 1, right? Then when we generate this number for LUI, then we need to use the number which is increased by 1. Okay, so instead of 8, we need to use the 9 in this case. Do you understand? So it is because if this MSB is 1, if at lower part the MSB of lower part is 1, then the hardware will apply the sign extension like 1, 1, 1, 1, 1, 1. So it should be FFFFF. So it's equivalent to the -1 to the upper part. So in order to make the correct number, then we need to put the FETC 9, not 8. So it's incremented by 1. Then we use the add I, and then -341. Then we can store the correct value to the register. Okay. So just to remember that, so add I. So when RISC-V instructions handle the immediate numbers, then these immediate numbers are signed numbers. Also, the instructions are data, right? And then the size of instruction is fixed. So which means the size of immediate numbers is also fixed. Okay, so it can be 12-bit or it can be 20-bit. Okay, so you need to remember this. Okay, and then let's learn about the logical and shift instruction. So what are logical instruction or shift instructions? So in C, we can use the shift left or shift right operation. So this is the operator in C. and then in means the shift left, and then it means shift right. So what is shift left or shift right? It is a bit shift operation, right? So even though we just use the decimal number in a high-level language code, but these numbers are translated into the binary numbers, right? So actually, it is because the CPU can only understand the digital signal. So shift left represent the bit shift operation. So if we use this operator, like the shift left by 2, then the 2 bit is shifted to the left, and then zeros are inserted to the empty spot, and then shift right. The bit is the bit shift operation. Also, because we are handling the digital numbers, okay, binary numbers, we can use the logical operators in high-level language code, like and, or, exclusive or, and not. Okay, so this AND operator performs the bitwise, the bit by bit AND operation. Okay, so it just performs the AND operation for each bit. Okay, bit by bit, and then or is the same, exclusive or is the same, and then you can also use the not operation. So also Java has the similar operators, right? And then in order to support these operations, the RISC-V also includes the shift instructions and logical instructions. So these are RISC-V instructions. SLLI, SRLI. So what is I? This I represent the immediate number, right? Because we can just use we frequently use this constant number for shift operation. And then for the AND bit by bit AND operation, the RISC-V supports AND instruction, and then AND I, or, and or I. So you can understand that this I represent the immediate numbers, right? Immediate, and then exclusive or, and then exclusive or I. Uh, RISC-V does not have not not instructions. Why? What is not? How can you implement the not operation? So it is the bitwise not. So it just inverts the every bit. Right? How can you implement? We can use the exclusive or. Is it because a exclusive or is similar? It's equivalent to the not a, right? Right? Also, we can uh how can I? So we can implement this not operator using subtractor. How? Minus a. So in order to make the minus a, we need to use the a bar plus 1. So minus a minus 1 a, right? Okay. So usually, so we can use the exclusive or to implement the not operation, the bitwise not operation, right? So this is the example. So the bitwise and so it's useful for masking bits. So what does that mean? So this is the number, and then uh, we want to extract a part of bits from a number. So then we can just apply the and this masking bits. Then we can just extract the corresponding bits from this number. So bitwise OR is useful for combining bit fields. So what does it mean? So we want to combine these numbers and these numbers. Then if we just apply OR operation, then we can just make this number. And then this is the bitwise exclusive OR. And then as I mentioned, this is useful for inverting bits. Okay. So A exclusive OR -1. So what does it mean? This is the -1 is the all F, right? As I mentioned. So A and all 1, 1, 1, 1, 1, 1. So the bitwise exclusive OR. So this is the NOT, bitwise NOT. Okay. So this is the example code. So you can check this code. That is the source register, and then there are two source registers. So either here, source register 1 and source register 2, and then this is the destination register. So what does that mean? And S3, S1, S2, it just performs the S1 and S2 equal S3. Okay? So you can just understand like this. So the logical instruction is very simple. Okay? So also we can use the immediate instruction for AND I or I and exclusive I. And then, so like the add I instruction, this AND I or I and exclusive or I in handles 12-bit signed number, right? Then how can we apply this bitwise logical operation? So like the add instruction, add I instruction, we need to apply the sign extension for the 12-bit immediate number. So you need to remember that. So in the RISC-V instruction, if the immediate numbers are used in an instruction, then these immediate numbers are signed number. And then when these signed numbers are used for arithmetic or logical operations, we need to apply sign extension, right? You need to remember this. So in order to, so when we use this number, okay, it's a signed number, and then this, this is the negative number. Then when you apply the bitwise AND operation, then firstly we need to apply sign extension to this immediate number. So we need to make the 32-bit number from 12-bit number, right? 12-bit immediate number. Then we can apply the bit by bit logical operation, like AND operation, okay? And shift. The shift operation is also simple, okay? Uh, so actually we can just shift the number of bits to the left or right. So and then there are different kinds of shift instruction, like shift left logical, and then shift right logical, and then shift right arithmetic. So SLL represent the SLL, right? Shift left logical. Okay. So what does that mean? So this is as I mentioned, it's a bit shift operation, but it's to the left. So and then, so for example, so this is the number 110 110. Okay. Then if we just perform the shift by 2 to the left, then this one is removed, right? And then 100010, and then there is no numbers here. Then we just fill these empty bits using zeros. Okay. So this is the shift left logical instruction, and then shift right logical, it's the same. It's the shift right operation. It performs the shift right operation. And then for the empty bits, we just fill 0. Okay? But in the shift left logical, then we just fill zeros to the LSB. It's a lower bit, right? But in the shift right logical, if we just perform the shift right, then we can find empty bits in the MSB part. Now what's the problem? If the target number is the signed number, and so why when do we use this shift operation actually? When when shift left logical. So actually shift left logical is equivalent to the multiply by 2 to the power of n, the power of 2, right? So in a CPU, so CPU handles the binary number, and so the shift left operation is equivalent to the multiplication with the power of 2, right? Right. So actually, the shift left by 2 is equivalent to the multiplied by 4. And then shift right is equivalent to the divided by power of 2, right? So, but problem is that if this number is the negative number, then if we just performs the shift right logical, then the MSB is changed to the 0. So what does that mean? It was negative number, but when we perform the shift right operation, then it is changed to the positive number, right? So so in in order to support this operation, the RISC-V also has the shift right arithmetic instruction SRA. So when it also performs the shift right operation, but it fills with the MSB, assigned bit. So for the empty slot, so for empty bits, so shift right arithmetic just fills with the MSB, the signed bit. Okay. So this is the SRA. So that's why the shift right has the two different kinds of instructions, right? Shift right logical, it just fills with the 0, and then shift right arithmetic. So it fills with the sign bit. Okay. Okay. Uh, so we can also use the immediate number, but as I mentioned, the RISC-V just handle the 32-bit data, so we cannot use the very large numbers. Okay, so shift amount is immediate. We use the immediate numbers between 0 to 31. Okay. Okay, this is the shift instruction. Okay, then let's learn about the branches and jumps instruction. So as I mentioned, uh, so until now, so we learned about the arithmetic instruction, right? And then logical instruction, and then shift instruction. Okay. So and then these instructions handle register operands, right? Or immediate numbers, right? And then we learned about arithmetic like add, sub, multiply, or divide. division, and then logical and or exclusive or, and shift SLL, SRL or SRA, okay, instructions. Also, we learned about the memory instructions like load and store instruction. The load and store instructions access memory. Okay, memory using addresses. Okay, now we will learn about the branches and jumps. Then, what is the target of branches and jump instruction? So, why do we use the branches and jumps? So, for example, because we frequently use the control flow or control operations in our high-level language code. So, for example, if A equal B, then C equal A plus B, else C equal A minus B. We frequently use the if-else statement in C, in a high-level language code, right? So what does that mean? It means based on this condition, this operation can be performed, or if this condition is false, then other operation can be performed. Okay, but this is determined by this condition. So right, then how can a processor execute this operation? Actually, we don't know. We don't know this condition, right? We can just know the result of this condition, during the runtime when a program is executed. So what does that mean? Our code includes this part and this part, right? Like add CAP or sub CAP. So our code includes the add instruction and sub instruction. And then, the instructions are in memory, right? Then how can we execute this instruction or this instruction? How can you select? How can you control? So these instructions are in the memory. And then based on the condition, so we can execute this instruction or this instruction. How can you control? We can adjust PC, right? So we learned about the program counter, right? So program counter is an address of an instruction, right? And then the PC has the address of instruction which is being executed. Okay, so if we just adjust the program counter value, then we can just execute this one or this one. Okay, so branch and jump instruction is actually required for supporting this control operation. Okay, so and then this operation is frequently observed in our code. And then what is the target? What is the target of branch and jump instruction? It changes the program counter. So branch or jump instruction change the program counter. So you need to understand this. So we are learning about the different types of instructions. So arithmetic, logical, shift instructions. So it just use the register data or immediate numbers, and then these instructions change registers, right? Because the destination is the register, right? And then how about the memory instructions? The memory instructions can access memory, and then it can change the register or memory. So load instruction change this register, and then store instruction change the memory, right? Because it depends on the direction of uh, the data transfer direction between register and memory. And branch and jump instruction change the program counter. Okay, so you need to remember this. By changing the program counter, we can control the flow of instruction, the instruction execution flows. Understand? Okay, so let's see the example. So as I mentioned, it changed the PC. The target of branch instructions is program counter. So it changes program counter value. If the program counter value is changed, then the instructions which will be executed are also changed. So also there are two types of branch instructions: the conditional branch or unconditional branch. So conditional branch checks the condition of two operands or two variables. Okay. So and then based on the condition may be true or false, right? And then it performs branch instruction if the condition is true. Okay. Okay. So there are different kinds of branch instructions, but you can find that only the condition part is different. So BQ is the branch if equal. So it means that if A is equal to B, then the condition becomes true. If not equal, B and E not equal. So it's A is not equal to B, then condition is true. LT it's less than. So if A is less than B, then the condition is true. Greater than or equal. So A is greater than or equal to B, then it condition becomes true. So if you see the conditional branch, then the format is the same, but only the condition part is changed. Condition part is different. Unconditional. So there is no condition. It just changed the program counter. Also, you can find the different types of instructions. Okay. So actually, this instruction, usually the conditional branch is also called the branch instruction, and then unconditional branches are called the jump instruction. Okay. So why branch? Because it looks like, so when we encounter branch instruction, then the execution flow is can be go to this way or this way. So it looks like a branch in a tree, right? So that's why it's called the branch. Okay. So conditional branch, and then usually we call this is also branch instruction. Jump, conditional branch is the jump instruction. Okay, so let's see the example. So you can find the BEQ here. So it's what is BQ? It's a branch if equal, right? Equal, right? If you see this branch BQ instruction, then you can find that it has the S0 and S1. Okay. It handles register data, and then also you can find the target. So what is this target? And then you can find the target here. So this is called the label. And then label just to represent the program counter value of this instruction. Okay. So we can use the label in a RISC-V assembly code. Okay, so you can find the label here. Okay, if the branch instruction is handles the two register data and one label is a target, and then you can find the label here, the target of the branch instruction. Okay, so what does that mean? So actually, as we learned, every instruction has program counter value, right? Address, because the instructions are in memory, right? And then PC is the address of an instruction. So let us assume that the PC of this instruction is P. Then what is the PC of next instruction? It is the P plus 4. Why? Why? Because the size of instruction, the size of a single RISC-V instruction is 4 byte, right? So this instruction occupies the 4 byte of memory space. So the next instruction will also will start from the P plus 4. Okay, address P plus 4. Then what does that mean? The PC of this instruction is P plus 8. Also because the PC is a P plus 12. So program counter looks like this. So when a CPU execute these instructions sequentially, then how can we execute these instructions? Firstly, the PC is set as the P, right? Then this instruction will be executed. After that, we just increment the PC by 4, right? Because then the PC has the P plus 4, right? Because we just increase the PC by 4. Then a CPU then will execute the next instruction. So instructions are executed like this. So PC values are changed, the program counter values are changed, then the CPU execute the instructions pointed by this PC value, the program counter value. So you can understand like this. Okay. So, and then a CPU just increase the PC also by 4. Then next instruction, SLLI is executed. And then plus 4, PC is increased by 4. Then BQ will be executed. But you know, this is the branch instruction. So the meaning of this branch instruction is that it reads data from the S0 and S1, and then, you know, the condition, the equality is checked. So we just check the equality. And then if the condition is true, then it jumps to the target, this part. So what does that mean? Oh, this branch is executed. Check the condition. Oh, condition is true. Then PC is updated as target. Do you understand? Do you understand? So you need to understand that a CPU just to change the program counter value, which then using this program counter value, the instructions are fetched. So what does that mean? So actually, we can just find these instructions in the memory, right? Then the branch instruction, oh, it jumps to the target. It means the PC is updated as the target. Okay. Then, oh, using this target, we can access this instruction. Then a CPU will execute this instruction. Okay. Do you understand? So what does that mean? Because it jumps to the target, these instructions will not be executed. Right? That's a good question. So his question is that our target is the 32-bit address. Actually not, right? Uh, you know, like the immediate. So this is the immediate number. Okay, actually, so in an assembly code, we can directly use this label. Okay, so assembly instruction is a little bit different from the machine instructions, right? So actually in assembly code, we can directly use the label name. And then this label just to represent the program counter. But actually when this assembly instruction is encoded into the machine instructions, this part is changed to the immediate number. Okay. So and then this branch instruction uses 12-bit immediate number. Actually, you know, the PC is the 32-bit, but the branch just handles the 12-bit immediate number. So actually, the branch calculate this target, the target PC using the program counter of this branch instruction plus immediate number. Okay. So it looks like the offset from the branch instruction. Okay. So that's a good question. So it is because, as I mentioned, so this immediate number needs to be included in the instruction, right? But you know, actually we require additional fields to represent this instruction. So actually the branch instruction has only 12-bit for representing this target. So we can use the only 12-bit immediate number for representing this target. Okay, a good question. Okay, this is another example. So it's a B and E. Okay, but this example shows that the branch is not taken. So in this example shows that branch is taken. So taken means that the condition of branch is true, then the PC is changed as the target of branch. It is the meaning of branch is taken. Branch is not taken. The condition is false. Then what will happen? This is P plus 4, P plus 8, P plus 12, P plus 16. If the branch condition is false, then it does not jump to the target, and then next instruction is executed. Okay, so the CPU just performs PC plus 4, right? Because the PC plus, so when we just increase the PC by 4, then it means it will execute the next instruction. What is the next instruction of a branch? The next instruction of a branch is add I, and then the PC value of this add I is P plus 16. Okay, so if the branch is not taken, the condition of branch is false, then next instruction will be executed. Okay, this is the behavior of a branch instruction. So if the branch condition is true, then it jumps to the target. If the branch condition is false, next instruction will be executed. So this is the behavior of branch instruction. Okay, jump, just jump. Okay, it's the unconditional. So in this example, just jump to the target. Where is the target? Target is here. So PC is updated as the target unconditionally. Then we can execute this instruction. So this is the unconditional branch, or it is called a jump instruction. So we can use the branch instructions to implement conditional statement such as if else and then loops like while loops or for loops. So let's see the example. This is the if statement. So if I equal j, then it performs f equal g plus h. Otherwise, no, not otherwise. And so this is the conditional execution, right? So conditionally, this statement is executed. Then this is the common part. So it looks like this. So we just check the I equals j. Then if this is true, then it performs the f equals g plus h, and then is merged. Then f equal f minus I. So how can we implement this? So if you see this condition, then you can think that, if I is equal to j, right? The condition is we just check the equality of I and j. And then if this is true, then this one is executed. False, not false. This is the common part, as I mentioned. Okay. Then how can we implement this? So you need to understand the behavior of branch instruction first. The behavior of a branch, if the condition is true, then it jumps. Okay? What is the jump? Jump means that this operation is skipped. Do you understand? So if you see the compiled RISC-V instruction, then you can find that instead of BQ, we use BNE. Why? Because if the condition is true, then this is performed. If not true, then it's skipped. So we need to implement this one. Skipped. Skipped means it jumps to the other part, the common part. Do you understand? So we can, instead of equality check, we just check the inequality. Okay. Then if this condition is true, then this part is skipped. Skipped is a jump to this one. Solve. And then if this I equal j, then it becomes the false, then add instruction is executed. So it implement this control flow. Okay, so this is the if statement. If else, so this is the if else, then you can also implement the if else using the BNE and jump. So unconditional jump, because if else has the true part and false part, right? So it looks like this. This is the some branch instruction, and then it's a true and false. Then it just performs the different operation, and then it is merged. So control flow looks like this. So how can we implement this? Sometimes, but based on the condition, A can be executed and or B is executed. So we can also skip some instructions, but after that, the control flow is converged actually. So it's converged. Okay. So we also use the BNE. Okay. Condition is then if this condition is true, then jump to this one. Okay. Otherwise, add instruction is executed, and then you can find the unconditional branch is a jump instruction. Okay, because if we do not have this one, then this instruction will be executed. So we need to jump to this point. Done. Okay, so this is the if else statement. While so while just check the condition, and then if the condition is true, then these statements are executed, and then otherwise, then these statements are skipped. So skipped means that to jump to the different target, right? So you can find you can find the while label here, okay? And then this is the condition check part. And then if so you can find even though in this example we use the not equal, but you can find that we use the BQ, because if the condition, so if when we use the branch instruction, if the condition is true, then it jumps to the other instruction. It is similar to the skipping some instructions. So there are instructions here. So we just skip these instructions. Okay. So if this condition is false, then these statements are skipped. Okay. So you can implement this. You can condition check, and then if the condition is true, then you jump to the done. It's a skip. And then this statement is equivalent to this part. And then also you can find the unconditional jump to the while. Okay, so this is the while statement. For it's similar, right? You can find the BQ. So actually for just check this condition, right? And then if this condition is not true, then we do not execute this statement. So condition also use the BQ, and then it does check the state condition, and then done is skip jump to the done. Okay. Okay, we can implement the for statement like this. This is another example. So also you can also check the C code. So you can find the compiled C code. So this is another implementation. So this implementation shows some new instruction as SLT. Okay, but but actually the SLT means the set if less than. Okay, so set means, so digital system, set means that we just put one to a certain variable. What is reset? Make the variable 0. Okay, so SLT, it means that set if less than. Okay, so it means it's similar to the comparison instruction. Okay, so compare the two values, and then if the condition is true, then we just set the target register. So this means the SLT. So, but actually we don't use the SLT in this case. But this slide shows some another version, another implementation of a for statement. So which means we can use the SLT. So which means we can just set the register based on the condition, and then we can check the value of a register. So you know, in the PQ, just compare the T2 with the 0. Okay, and then actually T2 is set or reset based on the this condition. Okay, this is another implementation. So actually, in the for statement example, so I just showed the example of example assembly code which has the B branch instructions in the top of the loop and then jump instruction in the bottom of the loop. But actually, we can apply this iteration loop differently. So actually, this is the exact uh, translation. The exact translation means that uh, actually for loop, it's true. So it's correct. We need to firstly check the condition of a variable, right? But if we know that, oh, actually this for loop will be executed at least once. The compilers can analyze this, right? Actually we just know the this initial condition, right? So if we compilers analyze this initial condition and then this condition in a for loop, then compilers can know, oh, this loop will be executed at least once. Okay. So in this case, the branch instruction can be located in the bottom of the loop. For example, loop is here, and then the sum is here, and then B branch instruction like B and E or some other part is here. So we can implement the for loop like this. So because I showed the example of for loop like this, but actually the compiler can generate the code like this. So it means this statement is executed and then check the condition and then it jumps to the start point of this statement for loop. Okay, so we can implement the assembly instructions or assembly code like this. Okay. Okay, signed and unsigned. So the branch instruction has the BQ, BNE, and then BLT and BGE. So actually, in order to check the equality or not equality, then we can just check each bit. We can just compare each bit value, right? But LT and GE, so we need to check the A is less than B or A is greater than B. So what does that mean? We may need to compare signed numbers or unsigned numbers. So it is because if the A is the unsigned number or B is the unsigned number, and then if the MSB is 1, then A is larger than B. It's greater than B, right? Because in the unsigned number, each bit represents the positive numbers, right? But if we use the signed number system, right, then if the sign bit, we need to check the sign bit, right? So if the A is negative number and then B is a positive number, then if the MSB of A is 1 and then MSB of B is 0. So in this case, A is less than B because A is the negative number. So what does that mean? When we use BLT and BGE, then we need to distinguish the target numbers. Target operands are signed numbers or unsigned numbers. Do you understand? So the sign the default is the signed numbers. Okay, so when we perform the signed comparison, then we can use the BLT or BGE, or if we just performs the unsigned comparison, then we need to use the BLT-U and BGE-U. So think about the C code. So we just declare a variable using the integer. Then what is this integer? It is the signed integer. So default is the signed number. If we just declare the unsigned integer, then we need to add the unsigned int. You need to use the unsigned int. Okay. Then A is the unsigned number. So just to remember that the default is the signed number. And then, but sometimes our code needs to handle unsigned numbers. So in this case, we need to distinguish unsigned numbers or unsigned numbers. Okay. Basic block. So this is also some important concept in a code. Okay, we have only 2 minutes. So the basic block. So this is the definition of a basic block. So basic block is the sequence of instruction with no embedded branch except at end, and then no branch target except at beginning. So this is the definition, okay? So it's a definition, so you need to memorize. Then why? Why do we need to know, oh, this is the basic block or not? So it is because, let's see this example. Let's think about these instructions. If this instruction is executed, then we know this instruction will be executed, and this instruction will be executed. And then also this instruction will be executed. So if we just see these instruction sequences, then we can know that, oh, these instructions will be executed sequentially for this group, right? But actually, here, then the instruction flow can be changed, right? So it can jump to this one, and then or the other instructions can be executed. So the basic block guarantees that inside of the basic block, then if the first instruction is executed, then other instructions will be executed sequentially. The basic block guarantee this. Then this is important for compile optimization. Okay. But so this time, so just to memorize the definition of a basic block. Okay. So I will explain about the basic block on the next class also. Okay. Okay. I'll stop here and then see you in the next class. 감사합니다.